Today we begin our discussions of modal logic, focusing first on propositional modal logic. And then after we complete propositional modal logic, we will turn to quantified modal logic. Quantified modal logic is a small enhancement of propositional modal logic and raises interesting philosophical issues that we will focus on a bit more than we do the philosophical issues concerning propositional modal logic. Here, though, in this first video concerning modal propositional logic, we'll try to get all the way through the proof theory for modal propositional logic. So first, we're going to talk a bit about the history of modal logic. We're going to talk some about the philosophical issues concerning various types of necessity and how to understand the diversity of types of necessity. And then after we do that, we will turn to the syntax, the additional operators that we need, the additional logical symbols that are needed, the axioms for various modal systems, and what the proof theory looks like. So first, let's talk about the history. The history of modal logic begins with C.I. Lewis. C.I. Lewis was a philosopher at Harvard in the early part of the 20th century, and he began investigating modal logic in the early, maybe the 19-teens, the second decade of the 20th century. Lewis was concerned that the material conditional was too weak for certain important claims, such as that one claim entails another. If you think about the material conditional, A arrow B is true in every case except where A is true and B is false. But that doesn't require there to be any interesting connection at all between A and B. It's simply a function of the truth values of the two claims. So, for example, think of mere chancy coincidences. You got up at a certain time this morning. Moscow is still the capital of Russia. Given that both of those claims are true, the implication relation, characterized by the material conditional, holds between the two claims. If you got up at the particular time that you did, then Moscow is still the capital of Russia. But there's no connection at all between the two claims. I expect there are forces trying to move capitals around in various countries around the world. I wouldn't be surprised if there's political groups trying to move the capital of Russia around as well. But there's no interesting connection between the time that you get up and the success or lack of it of these particular political movements. That concerned Lewis because he thought there was an important sense in which some connections are more than mere chancy coincidental connections. And the material conditional, he thought, was not suited for expressing that. So what is it for one claim to entail another? Lewis thought that was more than there being a material implication relation between the two. He thought you needed the implication to have a kind of necessity to it. The material conditional is also, it seems, not well suited for claims about necessary connections. So you say oxygen is necessary for life. Now, if you remember how you did translations of sentences in ordinary English into the formal apparatus of first-order logic, if you had oxygen is necessary for life, you put the necessary condition in the consequent, and you put the other item in the antecedent. So, if you use O for oxygen and L for life, if you say oxygen is necessary for life, that would get you L, arrow, O. But that's just a material conditional. It has no more necessity to it than the connection between the capital of Russia and what time you got up this morning. So Lewis thought oxygen is necessary for life in a way not captured by the sentence L, arrow, O. Same thing for doing your homework is necessary for passing. These claims have something more substantive in terms of the connection between antecedent and consequent than can be captured by the material conditional, according to Lewis. That is, after all, what it means to say that the connection is necessary. So here's a fun example that supports or at least lends some credibility of some sort or other to Lewis's concerns. It's a fun example from Dorothy Edgington. So here's the first premise of an argument. If God doesn't exist, then it's false that if I pray, they will answer my prayer. Now that certainly looks true. If God doesn't exist, how could God be answering anything? Things that don't exist don't have causal powers of any sort. So if God doesn't exist, then it's false that if I pray, they will answer my prayer. Now it turns out Dot Edgington is an atheist, so the second premise is true of Dot. We can take her word for it. I do not pray. So this is in the voice of Dot, and hence the referent of the word I is to her life and experience, and she claims she doesn't pray. What follows from that? Well, what follows is God exists. That's a particular example of modus tollens at work. It's a very cute example, and it shows something about what C.I. Lewis was concerned about. If all we have are the resources of the material conditional, we end up with arguments like this. The premise is true, the first premise. The second premise, we can take her word for it, is true, but this is a lousy argument for the existence of God. So suppose we agree with C.I. Lewis that we need to introduce the language of necessity into our first-order logic. We need to supplement it in some way by discussions of the notion of necessity. The question about what types of necessity and how to do the supplementing, there's both a logical issue about how we're going to supplement our logic. There's also philosophical issues about necessity itself. So I'm going to give you one approach for thinking about this. It's certainly not uncontroversial. But the first thing to notice is that there are various types of necessity. On one view of this matter, the types of necessity are relative necessities and absolute necessities. The idea that some necessities are relative and one is absolute is an idea that we can get from Thomas Aquinas. So it has a relatively ancient history to it, but it's not without its controversies. But let me characterize how the view works and how we're going to introduce the language of necessity into our logic without succumbing to the issues that plague some accounts of necessity in terms of relative and absolute notions. So think about what Aquinas might have been thinking. Some people, here are some plausible claims. Some people can't pass a logic exam. Maybe that's not true, but it certainly looks like it's true of some people. Sometimes I say, I can't make your graduation event. There's a kind of impossibility here. It looks a little bit like maybe the impossibility in the first premise, But if you think maybe the kinds of impossibilities are somewhat different, that looks plausible as well. Why can't you make your graduation event? The answer to that will be something about conflicts on my schedule, that sort of thing. Why can't some people pass logic? The answer might have to do with certain mental limitations that the person has, not problems with scheduling. So that's a different kind of necessity. We can't travel to Mars yet. You can't change the past. All of these look like they might be different kinds of impossibilities. You can't square a circle, that's even different. You can't change the past and you can't square a circle, but those aren't exactly the same kinds of necessities or impossibilities. You can't turn lead into gold. Notice what we've got here. You can't square a circle is a certain kind of mathematical impossibility. You can't turn lead into gold is a certain kind of scientific impossibility. You can't change the past appeals to a notion of necessity that in the Middle Ages was called accidental necessity. And it's not either the kind of impossibility of math or science, because the past comes to be impossible to change as we move through time. So take the events that recede into the past. At one point, those events were future events. At another point in time, they were present events. Once they recede into the past, they become impossible to change. So at some points of time, those very events could be changed or affected and weren't the kind of thing that can't be affected, can't be altered by our decisions. It's hard to talk about this and get it right, but the point is the future is open, the past is closed. So the events that are now future to us are open in some sense, but once they recede into the past, they take on a different characteristic. That's why the medievals called this accidental necessity. Notice that no such change in status occurs with the necessities of math and science. The impossibility of squaring a circle is something that's an eternal truth. The impossibility of turning lead into gold is a result of certain scientific necessities, we might say. Now, the stuff about traveling to Mars or not, that looks like a technological impossibility. It's not that there's anything scientifically impossible about traveling to Mars. It's just that we don't have the technology yet to do it. I can't make your graduation is none of those sorts of things, and the inability to pass logic might be a little bit like not being able to turn lead into gold, because it's a psychological impossibility for some people. And that might be a kind of scientific fact about some people. On the other hand, the laws of social sciences and the laws of the hard sciences might not involve the same kind of necessity. That's an open question. In any case, the first one, some people can't pass a logic exam, is a necessity sourced in the social sciences. You can't turn lead into gold is sourced in physics and chemistry. You can beg, but you can't borrow. I don't even know what to say about that one. It's just a nice saying, and it has two modal notions, so I put it on the list. Trump might resign. That's a more interesting one. Now, if you think about it, I think you're almost certain that Trump's not going to resign, but he might. The language of might and the language of can are interestingly different. The usual use of the language of might is epistemic in a certain way. It's relative to what we know. or something like that, maybe relative to what we're completely certain about. That means it can vary from one person to another. If we go to fictional contexts, the director might think Bond might be in Zurich. The secretary might know that Bond is hiding in the office next to them, and so she rejects the claim. Bond can't be in Zurich. The director says Bond might be in Zurich. The secretary says that's false. He can't be in Zurich because he's in the office next to us. That's an interesting use of an epistemic modal. The epistemic possibility exists for the director that Bond is in Zurich. The epistemic possibility doesn't exist for the secretary. Why? Because she just saw him in the office next door. So we need some way of systematizing our understanding of these various kinds of necessities. And to do that, we're going to introduce a relation, R. Typically, that's how we handle relativity in general. If morality were relative to, say, culture, then to say that something is right or wrong would be to say, relative to culture C, doing A is wrong. Relative to culture C prime, doing A isn't wrong. So we begin by systematizing in terms of this relation. We say, perhaps we agree with Aquinas, and we say some necessities are relative and perhaps some aren't, so that we can perhaps define different types of necessity that are relative in terms of some fundamental notion of necessity that's absolute. So perhaps Gnomological necessity, that's the kind of necessity that comes from the laws of science. The reason it's called gnomological is because nomos is the Latin term for law. So relative to the laws of nature, something can be necessary. That's gnomological necessity. We've already talked a little bit about epistemic necessity and possibility, accidental necessity and possibility. That has to do with the necessity of the past. And we've got various other types of necessity, psychological necessity and impossibility, as well as others. We can specify these by characterizing what the relation R is. What is it that these relativized notions of necessity are relative to? That leaves us with perhaps an absolute notion of necessity. So if gnomological necessity is necessity relative to laws of nature, and if there is a notion of absolute necessity, as Aquinas thought, then gnomological necessity might be absolute necessity plus laws of nature ruling some things out. If that's true, then absolute necessity is completely unrestricted, unrelative. One way to say this is to say it isn't relative to anything at all. That's what Aquinas claims. It's not clear that that's a defensible view, but that's one way of talking about this. We're going to bypass that, though. What we will do is not presuppose that there is a notion of fundamental absolute necessity, but rather what we will do is characterize some relation R so that all necessities are relative, and the one that Aquinas thinks might be absolute necessity, we'll just give a special characterization of R that will make that kind of necessity distinctively relative in a way different from all the others. That will leave some room in our formal apparatus for debates regarding the precise nature of absolute necessity, whether there is any such notion of absolute necessity, whether there is any notion of fundamental necessity by which you can define all of the other notions of necessity. Those are all deep philosophical issues that have to be explored. If you're interested in exploring them, talk to me in office hours about them, and I'll point you to some literature. If you're really interested in it and want to go explore, I'll be happy to give you extra credit for the course based on your work about fundamental notions of necessity. So once we get to this point, we will have some notion of necessity and some relation R, so that we'll be able to incorporate all the various kinds of necessities into a formal system that accommodates the variety in question. We don't want to presuppose anything. Certainly we don't want to assume that there's only one notion of necessity. So now we're thinking about how to supplement our language, the language of first-order logic. What additional resources do we need to try to start developing a modal propositional logic? The first thing we do is add 3 symbols. Actually, it's only 2 symbols that we'll use primarily, but I add the fishhook because I think it's a really cute symbol, and it was C.I. Lewis's preferred symbol for characterizing the necessity relation between an antecedent and a consequent. So if he were to write A necessarily implies B, we get first A implies B, and then if we want to say A not only implies B, but it does so necessarily, Lewis would write this: A fishhook B. We are going to just put a box out front of the conditional relationship between A and B. So the box stands for it is necessary that. It's an operator. The diamond is also an operator, meaning it governs a well-formed formula. So if you say diamond A arrow B, that says it's possible that A implies B. So let me get rid of my underlining. Those are the 2 fundamental relationships that we have to supplement our first-order language in order to yield a modal logic. Moreover, there's a relationship between these 2 or 3 new symbols for our logic. We can define the diamond in terms of the box. If you remember from our first order logic, we could do the same thing with the quantifiers. We could define the universal quantifier in terms of the existential, or vice versa, through what are called dual rules. And if you remember, there were 4 fundamental dual rules that you were allowed to use when you were doing proofs in first order predicate calculus. Here we get the same sort of thing. We get a dual rule for defining the box in terms of the diamond. The box is just the diamond with a negation before and after it. So something is necessary. If something is necessary, then it's false that its denial is possible. And if it's false that the negation of something is possible, then that thing is necessary. So the turnstile goes in both directions. And then we simply define the fishhook in terms of a box in front of a standard material conditional. Those are the only new symbols that we need in order to develop a modal logic. In addition to the new symbols, the stuff that plays a role in the syntax and in our account of a well-formed formula in this language, we need to develop a proof theory. For our proof theory, we need to know what system of logic we're going to be looking at. Now, Lewis had a number of different modal systems, characterized in terms of different axioms. They are now called System 1 through System 5. It's a completely unilluminating way of referring to the systems, but that's the way it goes. We're going to use other ones. We're going to begin with System K. The reason it's called System K, by the way, is because it's derived from the work of Saul Kripke. The problem modal logic had from its inception in C.I. Lewis in the beginning part of the 20th century was Lewis had a bunch of different axioms that you could endorse or not endorse, and then you got a mathematical system characterized by whether or not various axioms were included in them, and you could manipulate the symbols, but you had no way of connecting this up with ordinary notions of meaning and truth until you get a semantics. Remember, to have a logic, we have to have both a syntax and a semantics. So if all you've got is a syntax, an account of well-formed formulas, and a bunch of axioms, you have there a syntax for the language. But to complete the logic, you have to have also a semantics. It wasn't until 1963, 62 or 63, I'm getting confused on the dates. It doesn't matter. Kripke, at age 16, published a Semantics for Quantified Modal Logic. The simplest system that he talked about was System K. So we begin with System K, and then we'll supplement System K with various other axioms and characterize what those other systems are. So you get K by adding the following axiom to propositional logic. You're going to add two claims to propositional logic. The first is the rule of necessitation. The rule of necessitation tells you that there's a relationship between a sentence that's provable from no premises whatsoever and the necessity of those sentences. You can think of this as claiming that there's a relationship between a logical truth and a necessary truth. If phi is a logical truth, it's also a logical truth that phi is a necessary truth. Logicality implies necessity. We can put it that way. The second principle that we add is a distribution axiom. Necessity distributes across conditionals. So if one thing implies another, then the necessity of the first thing implies the necessity of the second thing. That is System K. Just those two principles added to propositional logic. We can then go further, characterizing systems M, S4, and S5, as well as another intermediate system between M and S5 called B. B is named after Brouwer. Brouwer is the one who suggested the fundamental axiom for System B, so it's called System B. System M is sometimes called System T. In fact, generally, I call it System T. System T, or System M, I think it's M in the Cider book, is characterized by this fundamental axiom. If a claim is necessary, then it's true. So, box phi implies phi. That's a hard principle to deny if you're understanding the box as anything like the ordinary notion of necessity. Of course, right now it's just an uninterpreted symbol. It's just a box. We have no clue as to what it means, so you pin down some of its meaning by supplementing system K with this fundamental axiom of system T or M. For S4, we add a further axiom. We add to T the claim that if something is necessary, then it's necessary that it's necessary. So boxes iterate. If you have one box, you can put as many as you wish. Let me pause and notice as well that there will be a reverse, an inverse version of this same axiom, as there will with other ones. So look at system T for a moment. Let me back up so that I can write it without interrupting the flow of the slides. So think about doing contraposition or transposition, I think it was called in first order logic in the notes that I gave you. So if you have transposition on the first axiom of system T, you get not phi implies not box phi. And if you think about the definition of the box and the diamond, you can probably see pretty clearly that not box phi is the same thing as diamond not phi. That will be provably equivalent. So not phi implies diamond not phi. Since phi is perfectly general, just drop the two negations off of it because this is a variable in the meta language for any formula whatsoever. And so if it's the same formula on both sides, then an alternative version of the axiom for system T is X implies diamond X. That's an interesting fact. It's also not surprising, if you understand the diamond, to express possibility. If X is true, then it's possibly true. Hard to disagree with that. So that's one sort of alternative way of expressing the T axiom. Notice we can do something similar for the S4 axiom. If we do transposition again, we get the negation of the doubled box implies the negation of the singled box. And now notice, let's take each of the negations and replace the box with a diamond. So we would get diamond, box, diamond, negation, box, phi, implies diamond, not phi. Now this isn't a proof rule, but notice you should be able to see that this will hold. Let's now redefine this thing in terms of the dual rule for diamonds and boxes. That will give us this. That's a pretty ugly diamond. Let's see if I can do better. So diamond, diamond on a formula implies diamond on a formula. So another way to express this distinctive S4 axiom is to say you can eliminate multiple diamonds. So if you've got diamond, diamond, X, that reduces to diamond X. And by repeated applications of that principle, you can eliminate as many diamonds in a row as you have out in front of a formula, regardless of how many there are. Finally, for system S5, the most expanded version of C.I. Lewis's 5 systems, we add to S4 the following axiom. If a claim is possible, then it's necessary that it's possible. I don't know if that claim sounds intuitively plausible to you, but in any case, that's the axiom. We'll see a defense of it once we get to the semantics for modal logic. But notice it's very hard to look at that one and assess whether or not it's true. Maybe you had the same experience when you looked at the axiom for S4. Suppose something is necessary. Did it have to be necessary? S4 says yes. So you look at something that's possible. Suppose a claim is possible. Does it have to be possible? S5 says yes to that as well. Now notice you can do the same sort of transpositive argument form that I used regarding T and S4 to come up with an alternative version of S5. I'm just going to show you that briefly. So you've got the transposition of the S5 axiom. If it's false that it's necessarily possible that phi, then it's not possible that phi. So then apply the dual rules first to the outside one. Replace it with box not. I'll leave the antecedent alone. I'm sorry. I think I will go ahead. I meant consequent. I said antecedent. And let's do the same thing to the consequent. Use the dual rule to replace not diamond with box not. Then do what we did before. Take the not diamond on the inside. You know, by the way, I'm repeating myself here, but you cannot do this in the proof theory for anything because none of our proof rules apply to parts of lines. But it will be provable that this holds. You just can't do it in one step. So now we have this version of S5, and notice the formula is perfectly general. So an alternative version of S5 says, if a claim is possibly necessary, then it's necessary. Whoops. You can't switch like that. Okay, if a claim is possibly necessary, then it's necessary. That's an alternative version of S5. And that may make you question S5 as well. The fact in general that something is possible isn't grounds for thinking that it's true. So the fact that something is possibly necessary, why would that mean that it's necessary? That looks like an instance of diamond P, arrow P. But you know that's a really bad argument. The claim of S5 is modal contexts are special. The possibility of a necessity is different from the possibility of a truth in general, because necessities are just one kind of truth. So the rule that's a bad rule for truth in general, diamond P, arrow P, doesn't carry over to modal contexts where the value for P is itself something that has a box on the front of it. So S5 claims if something is possible, then it's necessarily possible, which means the same as a possible necessity is itself a necessity. The possible necessity of a claim gives us the necessity of that very claim. Now, in between M and S5, we have S4. We can also do system B. System B gives us this formula. If phi is true, then it's necessarily possible that phi. It turns out, as we will see, that you can get to S5 by going from system T to S4 and then to S5, or you can also get to S5 in an equivalent way by going from T to B and then to S5. So you can get S5 by adding either B or S4 to T and then adding S5 to whichever combination you chose. But B tells us if a claim is true, then it's necessarily possible that it's true. So here's a question. There are two different ways to characterize the B axiom, just as we found with the other ones. I'll let you work this out for yourself, but here's an equivalent way of characterizing the B axiom. You can derive it from the original statement of B by doing transposition and applying the dual rules as we did in the other cases. When you do so, you end up with, if something is possibly necessary, then it's true. Now, if you think about those two different ways of characterizing B, you might have the following reaction. Many people do. I'm not sure I do, I'm not sure I ever did, but it may be I didn't have the distinctive reaction here because I didn't quite grasp what the sentence said. This sentence says, if a claim is true, then that claim is necessarily possible. That may strike you as a rather innocuous claim. Maybe it doesn't. Maybe it strikes you as a substantive claim, but it doesn't sound like that bad of a claim. If a claim is true, then you already knew it was possible. So maybe it has to be possible. B looks like it might say, if a claim is true, then it has to be possible. That might strike you as a pretty okay kind of claim. But then look at the equivalent way of expressing the axiom. If a claim is possibly necessary, then it's true. Well, you know that if a claim is necessary, then it has to be true. But if it's only possibly necessary, why would that get you that the claim is true? It looks, from that perspective, that the alternative characterization is saying something more substantive than the original formulation. So I asked in the notes, does one of these ways look more obvious to you than the other? If so, it's probably the first one that looks more obvious than the second. If you can contort your mind to see it in that way, good. It'll help you grasp one very common fallacy. It's the fallacy of confusing the necessity of the consequence with the necessity of the consequent. We'll talk about that more later. By the way, this name for the fallacy derives from medieval work on logic, especially in the work of Aquinas. I think he uses this very language. It doesn't exactly communicate in a very effective way, but you'll see what it's about later on, and it will become clear what the difference is. A consequence and a consequent are different things. If you have A arrow B, the necessity of the consequent would be the necessity of B itself. The necessity of the consequence would be something about the arrow itself, that somehow the arrow is really a disguised fishhook. More on that later. On the syntax side, our last step is to develop a proof theory. We'll have different proof theories by adding, first, different axioms, which will allow us proof rules from each of the axioms. So, for example, S4 adds this axiom, which we turn into a proof rule, which allows us to derive box phi from box phi. In general, that's how we'll treat axioms. We will take the axiom and turn it into a rule of proof. In addition to those extensions of our system, we need to add axioms, we need to add rules for each of the new logical operators that we're using. Now, you know we have two new operators in our system. We have a box and a diamond. We also have the fishhook, but we're simply defining that in terms of the box. So we're not going to treat it in terms of developing special rules. And if you remember our little rubric for additional logical apparatuses or apparati, we need both an intro and an elim rule for each. So we need box in, we need box out, we need diamond in, and we need diamond out. Two of these rules are extremely easy to characterize. Notice diamond out should just be this rule. If you got a formula that's boxed, you can write down the unboxed form of the formula anywhere you want in the proof. That's just the rule that we adopt using the distinctive axiom of system T. That axiom was box phi arrow phi. So our box out rule is just the proof rule analog of the distinctive axiom of system T. The other rule that's very straightforward is the diamond inversion. Diamond in is just the alternative expression of the fundamental axiom of system T. If you recall, we said an alternative way to express that fundamental axiom is if phi is true, then it's possible. So the rule of proof that we use is from phi, from any formula, you can always add a diamond to the front of it. So both the diamond in and the box out rule are very straightforward rules of proof derived from the fundamental axiom of system T. So those two are very easy rules to adopt. The harder question for us will be, the more complicated question will be, when do you get to introduce a box and when do you get to drop a diamond? Notice intuitively both of those are really bad rules of inference. So there's going to have to be significant complications to when we can use these rules. So the simplest version that you might think about endorsing is you've got phi on a line and you get to box it. That's a really lousy form of inference. The necessity of a claim rarely follows from the fact that the claim is true. Truth can be contingent. And so from the fact that a claim is true, it just doesn't follow that it's necessary. So you can't have a box-in rule that is perfectly general. It's going to have to be carefully controlled in order to be useful. Similarly for diamond out. Suppose that you've got a formula. Let me try to make that legible. Suppose you've got a claim that's possibly true. Actual truth rarely follows from possible truth, but that's what the simplest, most straightforward account of diamond out would be. You've got a diamond formula, you just get to drop it. Again, a lousy form of inference, so we don't want that. So we know what diamond in and box out look like. Those are very straightforward. The hard part for our proof theory will be, what are we going to do for the other two? In summary, here's what diamond box out looks like. Box elim is, if you've got a boxed formula, you can drop the box. Diamond in says, if you've got a formula, you can always put a diamond in front of it. What about the other two rules? All right, let's start with diamond out. So we're going to treat diamond out by analogy with how we treated existential elimination in the first system. So if you think about the analogy, you're thinking about the diamond as being like the existential quantifier. If you had an existential quantifier, you assumed something, you then proved that another formula followed, and then you discharge this assumption by concluding something else. In this case, since we're not using an existential quantifier, here's what we're going to do. We're going to say, assume you've got the claim that phi is possible. So just assume that phi is true. Now I'm going to characterize this in terms of the language of possible worlds, which is our semantic theory that we'll develop in the next video. But if you think about it in terms of possible worlds, to say that phi is possible just says there's some world in which phi is true. Some possible world in which phi is true. So what we're going to do is assume phi. In other words, we're going to go take the perspective of that world on phi. So we're going to work within world phi, world W, in which phi is true, and then we're going to show that psi follows from phi in world W. And so then we're going to discharge this assumption. We're going to say, look, if phi is true in W and it follows logically from phi that psi, then we can say that psi is possible as well. So from diamond phi, we get diamond psi because once we go to the world where phi is true, psi is derivable, provable from phi. So it has to be possible as well because W is a possible world. That's the intuitive idea of diamond elimination. And it's subject to the same restrictions we used for existential elimination. The line that cites the rule is annotated like this. Let N be a diamond formula. Then I will be the assumption that we discharge. M will be the formula that we add a diamond to, and N is the formula that had a diamond on it in the first place. So the annotation will look very much like what we used when we were doing existential elimination in the earlier system. All right, that's diamond E. We still have box in, but an interlude. We're also going to add operator exchange rules, which are just the dual rules like we had for quantifier exchange in first order logic. You can define the existential quantifier in terms of the universal quantifier. Here, we can define the box in terms of the diamond plus a couple negations, or vice versa, and those generate operator exchange rules. So if you have diamond phi, that gives you not box, not phi. If you have not diamond phi, that gives you box, not phi, and so on. Those are familiar dual rules to the quantifier exchange rules we used in first order logic. And then for each axiom distinctive of the relevant systems, we turn it into rule of inference. So T becomes box phi, turnstile phi. For S4, we get box phi, turnstile, box phi. And for S5, we get diamond phi, turnstile, box diamond phi. We still have the other rules, the distribution rule, where the box distributes across conditionals, and the rule of necessitation, where any logical truth, a theorem, can be boxed. Finally, the most difficult and complicated rule of all is the box intro rule. We complete our proof theory by adding it because we've already seen intro and the lim rules of every sort for boxes and diamonds apart from this one. What we're going to do for box intro is use reiteration rules, and then I'm going to give you some examples of how this rule in particular is to be used because it's the most difficult one to understand. So a reiteration rule can take one of three forms. We're only going to describe it for system T, for system S4, and for system S5. Now, the idea of a reiteration rule is you're going to reiterate something. So how does that work? Here's the characterization. Let's go through it very carefully. Given a proof of phi from a sequence of steps beginning with a premise justified by a reiteration rule for the system in question, conclude box phi. That's the form of the rule. Now, forget all the rest of this stuff for now. Let's just look at what the characterization of the rule tells you. What's the beginning of a proof of phi? What premise are we talking about? Justified by a reiteration rule. That's what the reiteration rules are telling you. So suppose somewhere in your proof you have box P. We'll also talk about what happens if somewhere in your proof you have diamond P. The reiteration rules allow you to put something down at the next line and justify it by a reiteration rule, either RT or RS4 for diamond formulas and RS5. Sorry, I said that wrong. RT and RS4 for boxed formulas, RS5 for diamond formulas. What you get to write down at the next line is given by the conclusion of the form of argument that the reiteration rule tells you about. So if you cite RT, you would write down P. Technically, P there is going to count as an assumption, but we'll worry about that in a moment. I just want you to see the form of the rule. So if you cite RT, you have to have a boxed formula, and then you drop the box for the conclusion. Now I want you to notice, some of you will already have seen this, the move from here to here, you could also justify not by RT, but by that T axiom itself. Because the T axiom tells you that if you got a boxed formula, you can remove it. The problem is, if you did that here and you were hoping to introduce a box, remember this is the box intro rule. You can't use the box intro rule unless you started by using a reiteration rule. So you have a choice here about whether to justify the move from box P to P by RT or by T itself, the T axiom. If your hope was to do box intro, though, you better use RT because you can't introduce a box without having used a reiteration rule first. Okay, the other thing that you can do, if you're going to use the reiteration rule for S4, is you just repeat the boxed formula. And similarly, if you use RS5, you just repeat the formula with a diamond in front of it. Now here's what I want you to think about. Intuitively, what you're doing in both of these cases is you're making an assumption, and then you're going to derive something from those assumptions. And then, once you do the derivation, you're going to put a box on the front of it. That's supposed to be the same formula that I just derived. What justifies being able to put the box on it? Well, for RT and RS4 rules, the idea is you started out with something that was necessary, and then you derived from the relevant assumption some formula, and so that formula is going to be necessary as well. In the case of P, diamond P for RS5, remember diamond formulas in S5 can be boxed. So if you have a diamond formula and you can prove something from a diamond formula, then you should be able to box it as well. So that's the details of how the rule works. Let's talk about the mechanics of applying the rule, the stuff that I said to ignore. So let's repeat again what we just said. You start with a premise justified by a reiteration rule. You prove phi from a premise justified by a reiteration rule, and then you get to box it. That's the way the rule works. Note here, the reiteration assumption depends both on the premise in question. Let's just use RT for example. So RT will have, if you're going to use RT, it has a premise, and you are going to get to cite RT to justify putting phi down. So now what's the assumption set for that line itself, for the conclusion? Well, the assumption set will be both this line number of the premise and its assumption set. So citing a reiteration rule puts that line in the assumption set, the line that's the premise. So suppose, let me clean this up a little bit. Suppose you're going to use RT. So you've got a premise, box P, And that's at line 8, let's say, just for assumptions. Then at line 9, you're going to appeal to line 8 and cite RT. What's the assumption set for line 9? It's 8 plus whatever's in the assumption set for line 8. And then when we discharge this assumption at line 9 with box intro, 8 will get to be dropped. So we'll be returning to the original assumption set. On the next slides, we'll look at some examples, and that will helpfully clarify what's going on here. So citing an assumption rule puts that line in the assumption set, which is then discharged by the use of box intro. So how do we annotate? Line M is the premise that justifies the use of the reiteration rule. That's what's going on in the table above. Line N is the reiteration assumption. That's the conclusion line in the table above. So line N is the reiteration assumption. Line O is the formula that we derive. So we derive some formula at line O, and then at the next line, we're going to put a box on the formula that we derived at line O. That's why it's called box intro. The assumptions for line N are all of the assumptions for M as well as line N itself. Line R is then justified by appeal to O, the box intro rule, followed by N in parentheses, because that's the assumption that you're discharging. So you're going to use whatever is at line O and put a box on it, discharging the assumption at line N. Okay, that's the technical details of the box intro rule. Let's look at an example of some proofs. I think we will use 3 examples here. The first example is that of a theorem. It's claimed that the following formula follows from no premises whatsoever. If box P and box Q are true, then the conjunction of the two is true and necessary. So if box P and box Q are true, then box P and Q is true. How do we prove this? Well, we're going to follow the same strategies that we used for first-order propositional logic. You have an arrow formula. The way to prove an arrow formula is begin by assuming its antecedent and try to derive the consequent. So let's begin by assuming the antecedent. That's what we do first. So we assume box P and box Q. If you see how to get from that to the consequent immediately, go ahead and do it. But I bet you don't see how to do it, because this is a formula that looks like you're going to have to build it by using box intro. You're not going to just be able to derive it by other rules without relying on that special rule. So if we were going to do it that way, you could, but how about if we just assume the opposite? If we assume the opposite, then at line 3, I'll fix this in the notes. That little a ought to be in the justification column. It's not part of the formula. I'll fix that in the notes. So first, apply operator exchange to line 2. That gives us diamond not in place of not box. Now I'm going to drop the diamond. To do so, I'm thinking about using the diamond elimination rule. And to use it, I assume the undiamonded formula as an assumption. So do that. So assume the negation of P and Q. Then use De Morgan's rule on that formula to get not P or not Q. Now, from line 1, using ampersand elimination, you can get box P. You can also get box Q from line 1, same rule. Then we can use the box E rule to drop the box from line 6, and we can also drop it from line 7, but let's not do that yet. Let's first do wedge elimination on lines, I left out a number there. It's line 8 and 5, not just line 5. Both 8 and 5 get us by wedge elimination, not Q. Now, once we get to not Q, we've got line 4 in our assumption set, so we really want to get rid of that. I'm choosing to do it here because I know at line 7 I've got box Q, and box Q is incompatible with not box Q. And not box Q is equivalent to diamond not Q by the operator exchange rules. So putting a diamond on at this point is going to help me end this proof fairly quickly. So I'm going to use the diamond elim rule to discharge assumption 4. So I'm putting a diamond formula on line 9. That's why I cite it. And line 4 has to be the undiamonded version of some prior diamonded formula, which it is. That's incorrect. It's not line 2, it's line 3. I've got to correct these mistakes in the notes, but I think you can see what's going on. I'll fix it in the slides, so make sure when you pull up the slides, you look at the latest version of the slides. All right, once we get to line 10, the way we did, we then apply operator exchange at line 11 to get not box Q. That contradicts line 7, so we use the contradiction between 11 and 7 to discharge line 2, which gives us box P and Q. And then we discharge line 1 by arrow introduction, giving us the formula we were asked to prove. Okay, that's an example of how we use diamond elimination in a proof. Here's another example. This is a case not of a theorem, because we've got the claim that not diamond A follows from 4 other claims. So the first thing we do when we do the proof is list all of our assumptions in order, 1, 2, 3, and 4. What do we do at line 5? Well, what I'm going to do is assume that the conclusion is false. So I'm going to assume diamond A. Now notice diamond A is a diamond formula. So at line 6, I can make an assumption of the undiamonded formula with the idea that I'm going to use diamond elimination to discharge this assumption at line 6. The reason I want to have the undiamonded version of line 5 is because if you look at these premises and just drop the box, it looks like I can derive a contradiction fairly quickly just by dropping the operators and doing a bunch of modus ponenses to get me to D. Once I get to D from the first 3 premises, the 4th premise converts to box not D, and box not D, by the distinctive rule associated with system T, gives us not D. So that's where I'm going to get my contradiction. So let's first remove the boxes from premises 1, 2, and 3 to give us A arrow B, B arrow C, C arrow D, and then start doing some arrow eliminations to get B, C, and D. Now I'm betting it's time to put the diamond back on. So what I'm going to do is put the diamond on to line 12 to discharge assumption 6. To use the diamond E rule to discharge 6 requires that 6 be an undiamonded form of a prior line. That prior line is 5. So I drop a diamond onto line 12, appealing to that rule. Now that I've got diamond D, notice at premise 4 I also have not diamond D, so I get to the conclusion by discharging assumption 5 by RAA, leaving me the formula I was supposed to prove depending only on 1, 2, 3, and 4, so that's a proof. Here's a third example. Suppose we have diamond, diamond P. Can we eliminate the extraneous diamond to get just diamond P? So here's a proof. Now I told you that that's an alternative version of an S4 axiom. This will constitute a proof of that because the explanation I gave you did not rely on rules. It involved doing replacements within parts of lines, and you can never do that in any proof in our lemon-style proof system. So we're going to prove it systematically, in this case, following the rules that were allowed. So first, we assume the premise. Then, at line 2, I assume that the conclusion doesn't follow, and so I'm thinking about RAA as the proof rule. So, first I do operator exchange on line 2. And now I'm thinking about introducing another box on the front of line 3. So I'm thinking about using box intro. And to do that, I'm going to use the reiteration rule associated with S4, because that will allow me to box that very formula. So to use RS4, I repeat line 3. So line 4 enters into the assumption set for line 4, and everything that's in the assumption set for the line that I'm repeating, namely 3, carries down as well. Now I'm going to do operator exchange to go back to the formula that I started with. The reason I did operator exchange in the first place, remember this from propositional logic. A negation out front of a formula paralyzes you. You have to get some way of moving that negation symbol inside, which is what I did at line 3. And then at line 4, I open a reiteration context, and then I go back to what I was looking for. Once I do that, I'm allowed to do box intro on line 5. So I cite line 5, I put a box on it, citing that rule, and I discharge line 4 in the process. So now I have box tilde diamond P depending just on line 2. Now I can use operator exchange on line 6 to replace the box tilde with a tilde diamond. That's useful because now 7 contradicts line 1, allowing me to discharge line 2 by RAA. So there's the proof that diamond P provably supports diamond P. Here are some sample problems that I will leave you with. If you want to do these, do them. You may do them for extra credit and send them to me as an email document, either as Word or PDF, to make it easy for me to grade them. And I'll take a look at them and see. So here's the way it's going to work. To get extra credit, you'll need to get all of the problems right. There won't be any extra credit for partial success. So these are worth practicing because these problems like this are going to show up on the second exam. But here's a whole bunch, maybe, how many of them? 2, 4, 6, 8, 9, 10, 11. So there are 11 problems here. If you wish to do these proofs for extra credit, do it, send it to me. If you get them all correct, I will give you extra credit. I haven't decided how much. But this is a good exercise, and if you can do these 11 problems, you are thoroughly prepared on the proof theory for modal propositional logic.